Okay, so I think the screen should be visible now, right?
Yes, ma'am.
Okay. So we were doing constrained optimization in the last week, and just a brief recap. So we had an optimization problem, a general constrained optimization problem. We took it in this form, where you minimize a function with some inequalities, subject to some inequalities and some equalities. And we sort of developed why we need the Lagrangian function, which is defined in this manner, okay, where you have some multipliers for each of the constraints, okay, so each of the inequalities and the equalities as well, okay. And we saw that, the notion of Kkt points, and we said that, if x star is, I mean, the optimum point, and if it is a provided it's a regular point. So by regular point we mean that you take all the active constraints, so the constraints at which, all the the constraints at which the inequalities are satisfied with equality, and you take the gradients of those functions, and they have to be linearly independent. Okay, so provided that is true, then we have this notion of Kkt point, and that x star is going to appear in a Kkt point. Okay, and the Kkt conditions were the following. Okay, so we wanted the gradient of the Lagrangian to be 0, and then we had this condition called the complementary slackness. This is something that we had seen even in the context of LPs. Okay, so this is one condition. So it's just mainly in this context, the purpose is to ensure that you only consider the active constraints in the Lagrangian. Okay, so that's why whenever the constraint becomes inactive, the lambdas become 0. Okay, so that was the purpose of this, and of course you should have that x star is feasible. So these were called the first order Kkt conditions, and these were necessary conditions for at optimality, provided some mild conditions are satisfied. Okay, and then we saw some examples of this, like how you can compute the Kkt point. So in general, it's not very evident like how you can just solve the system of equations. I mean, it's a nonlinear system again. So because of this lambda gix is 0, so you have to like inspect all possibilities. Like you have to take the cases where uh, all the constraints are inactive or some of them are active, and you take all possibilities, and that's how we solved we got the Kkt points. Okay, and then we saw things like, these conditions are necessary but they're not sufficient. Okay, so and then we also saw what happens when the regularity assumption is violated. So in some sense, the example that we had here was the case where the gradients were linearly dependent, right? So that's when the regularity assumption gets violated. So in that sense, you don't get a very rich space. So you're not able to you're not able to get grad f using the gradients of the active constraints. Okay, so that was some examples, and so then there were some examples where we saw that, a Kkt conditions could get satisfied even at the maximum. Okay, so where we left off last class is when I started moving into the convex optimization problems, in which case, instead of regularity, you can have another condition, the Slater's constraint qualification, which says that if you have an interior point, in terms of the inequalities, and of course equalities are all satisfied, so such a point is a Slater point. And if this happens, then the optimum will satisfy the Kkt conditions. Okay, and I wanted to also say that, if you do find a Kkt point here in the case of convex optimization problems, then you're guaranteed that it's going to be the optimum. Okay, so that's where we left off last class, and we were going to prove this. So let's just see a proof of this. So what I'm going to do now is I'm going to consider this optimization problem in this manner, and a case where it's convex. And suppose x star is a Kkt point, I'm going to show that it's also going to be optimum. Okay, so for the sufficiency part, there's no regularity or Slater's condition or anything. It's only needed for the necessary part. So the Slater's condition is needed only for the necessary part. Okay, so let's just begin. So you're given that x star is a Kkt point, and since it's a convex optimization problem, we have that f, g, these are convex functions, and h has to be an affine function. Okay, so otherwise there is no way that the region, the feasible region, cannot be convex. Okay, if h is not affine. So the equality conditions all need to be set. I mean, those functions have to be affine functions. Okay. So now we saw earlier that for convex functions, we have this first order property. Okay, so for any x in the feasible region, so let me call the feasible region as omega. So this omega is this set, okay, which satisfies, I mean, the set of all x which satisfies these constraints. So for any x in omega, since omega is a convex set and the function is convex, we have that this is true. So fx is greater than fx star plus the gradient fx star transpose x minus x star. Okay, so this is, if you recall, it's the first order convexity condition, and the same thing holds true even for G's. Okay, so in G's also, just due to the convexity of f and g, we have this. Now we also have that for the case of edges, those are linear or affine functions. So in that case, it gets satisfied with equality. It's not an inequality anymore. So Hjx is equal to Hjx star plus this function of the gradient at x star. Okay, so this is how we can compute. We can relate x, the function values at x and at x star. Okay, so this is just by the definition of convexity. Okay, now if you add these three sets of equalities and inequalities, what you're going to get is, so you multiply these with lambdas which are greater than 0 and multiply this with mu j's. Okay, so that sort of gives you the Lagrangian function. But anyway, let's just see what it gives if you add all of them. So what you're going to get is f of x plus on the left hand side, so f of x plus summation over all the inequalities, lambda I times gix plus summation over all the equalities, mu j times hjx. Okay, this is the left hand side, and the right hand side is, so this is going to be greater than fx star. So I'll just write the first terms together. So fx star plus summation lambda I gix star plus summation mu j hjx star. Okay, so that is the first terms of all the three inequalities and equalities. And the second part will give you, so the x minus x star is common. So you can just take this out, x minus x star transpose. Then you have delta fx star plus summation I lambda I gradient of gix star plus summation j mu j gradient of hjx star. Okay, so this is just got by doing this operation. The first inequality plus lambda I times the second inequality plus mu j times the third equality. Okay, so you get this. Now this function, this last part, what is this? Can you tell me what this would be?
Gradient of Lagrangian.
Yes, gradient of Lagrangian evaluated at x star, lambda, and mu. Okay, so take that, these x star, lambda, mu, that's the Kkt point. So let's say x star. So here, when we say Kkt point, it's a tuple, right? So it's x star, lambda, mu. So let's say that this is the Kkt point. And all these operations are with respect to lambda and mu for the Kkt point. Okay, so now, because this is a gradient of the Lagrangian, we know that since this is a Kkt point, this has to be equal to 0. Okay, so this whole part becomes 0. Okay, now what more do you know? Like, because it's a Kkt point, can you say anything more on these terms on the right hand side?
The lambda ij gi will be 0.
Yes, so this will be 0 because of complementary slackness. Okay, and anything you can say about this part? So this is edges are
That
the
will be
equal.
0.
This is also
Yeah.
0. Yeah, so these are 0 because edges are the equality constraints and x star is a feasible point, so that's why this is 0. Okay, now by the same logic on the left hand side, if you see, x is also a feasible point, so this term also becomes 0 because at jx is 0. Now what about this term? So one thing is it's a Kkt point, so we have lambdas are less than or equal to 0. Right? So lambdas are greater than or equal to 0, sorry. And g's are less than 0, right? Less than or equal to 0. So this whole term is less than or equal to 0, right? So what you have is, let me just write it here. So all these terms, this gets cancelled, this gets cancelled, this gets cancelled, and this whole term goes off. So what you're left with is f of x plus lambda I gix is greater than or equal to fx star. Okay, so this is a negative quantity. Okay, so so then what you have is, so fx star, so fx minus some negative quantity is greater than fx star. So what you have is fx star is going to be less than or fx. Okay, and this is true for all x in the feasible region. Okay, so this immediately gives you that x star is actually a global optima here. Okay, so that's why if you've managed to find a Kkt point for a convex optimization problem, then immediately you know that it is an optimum. Okay, so is this clear? Are there any questions on this? Any questions? Any concerns on this?
No, ma'am.
Okay, good. Okay, so yeah, so that's why, I mean, this is one of the reasons why, convex optimization problems, there's a special interest in this, because some many things are more simplified in the sense of the optimality conditions. Because of this nice structure, you have a better handle on how to solve these optimization problems. Like, for if it's not a convex optimization problem, for one, you need you are not guaranteed that once you find a Kkt point it is indeed going to be the optimum. You need something more there. And also things like these regularity conditions, I mean, this is anyway true. So if if these regularity conditions are not satisfied, then you don't really know what to do. Okay, so you don't have the conditions, I mean, you don't know what to look for. That is anyway true always. But the good thing about convex problems is, if you have these Kkt points, then you're guaranteed that you'll be able to find the optimum. Okay, so so the necessary conditions tell you when a Kkt point will exist, and the sufficiency conditions tell you when a Kkt point is an optimum. Okay. Okay, so now let's just see one example. I thought it's nice to show an example of, in convex problems, something that shows up in many applications. So that is this of entropy maximization. So are you guys familiar with entropy? Have you seen it in some course?
Just use the idea of entropy.
You've seen the idea of entropy. Okay, where have you seen, like which course?
Probability and statistics, and also Satna's course this semester for machine learning.
Okay, okay. Sure. So I guess you guys are familiar with entropy. You saw cross entropy loss, right? Okay. So I guess that you would have seen it in maybe logistic regression also, right? Is that where you saw that?
Yes, when we saw it in logistic.
Logistic. Okay. Okay, cool. So yeah, so the thing about entropy is, to give you some more intuition, it's capturing some notion of uncertainty in the system. Okay, so let's just take a discrete random variable. So this is x, and it takes support in one of these points, x1 to xn, and you know these points beforehand, and you want to find a probability distribution over x which maximizes the entropy. So the entropy for this random variable, like given this given some distribution. So let's say P1 is the probability that x takes a value x1, and P2 is the probability that x takes x2, and so on up to Pn. Okay, so let me just write it here. So Pi is the probability that x takes a value xi. Okay, so the entropy for this random variable is defined, it's for the distribution. So how you would define it is just the summation over all these support points, Pi log Pi. Okay, so what it's intuitively, it's capturing the sense of uncertainty in the system, or like suppose you have like all the probability. So it's like the point beforehand. So if you know the realization, so suppose P1 is 1 and all others are 0. So then what you're going to get is the entropy is just going to be 0. So that means there's no uncertainty in the system. Okay, because you know beforehand that x1 is the outcome that you're going to get. Okay, so so that's the notion of entropy. So what is the probability distribution that maximizes the entropy? This is something that we want to find, and let's just try to do this using the techniques of constrained optimization. So one thing is that this function h of x, this is a concave function in the p's. So I'll just call this h of p, okay, so that it also looks like a function of p, which it is. So usually it's entropy for the random variable given a distribution. So I'll just say it's h of p. So this is concave in the p's. Okay, and what we are trying to do is maximize h of p subject to p being a valid probability distribution, right? So what you will have is summation pi is 1, I equals 1 to n, and pi is greater than or equal to 0. Yes, this is the optimization problem we want to solve. Okay, now so in terms of the format that we are using, this would be just minimize. So it would be minus minimization of minus h of p, okay, subject to these constraints again. Okay, and pi greater than 0. So this the objective is just going to be summation pi log pi. Okay, so this problem we want to solve. So we are essentially solving this minimization. So this negative sign, so that you can apply, like once you get the value of the problem, it means you have to take the negative of that. So essentially the problem is this one. Okay, so let's try to write the Kkt conditions here. So here what's happening is, now this is a convex function. So minus summation pi log pi is concave, and this is going to be convex. So verify these facts. Okay, I will leave it for you to verify it. And this is an affine constraint. Okay, and this is also an affine inequality. So in essence, the feasible region is a convex set, and the objective function is convex. So we have a convex optimization problem. And so here we will just write this as minus pi less than or equal to 0, because that's how we have written the formulations. Okay, so now the Lagrange multipliers here, let me call this mu. And for each I, you have a Lagrange multiplier of lambda I. Okay, so let me write the Lagrangian now. So Lagrangian is a function of p, lambda, and mu. Okay, so can you tell me what the Lagrangian is? Anybody?
Summation pi log pi
Summation pi log pi, yes.
minus summation lambda I pi
Minus summation lambda pi, yes.
plus summation mu I pi minus 1.
So it is a single equality. So you will just have mu times summation pi minus 1. Okay.
Okay.
Okay, so now the first thing is gradient of the Lagrangian with respect to p is 0. Okay, so let's take it with respect to each I, right? So pi's. So what would the gradient be? So the first term will give you with respect
log
to pi,
pi
log pi
plus 1
plus 1, yes,
minus lambda I
minus lambda I
plus mu.
plus mu, and this is equal to 0 for all I,
Yes,
right? Okay, so then what this will give you is, if I just try to write pi, so log pi is just minus mu minus 1 plus lambda I. So pi is e power lambda I minus mu minus 1. Okay, this is clear, right? I mean, this just comes out from the Kkt conditions.
yes,
Okay, and so one thing to note here is by default you're going to get that this lambda, I mean this pi is always going to be greater than 0, greater or equal to 0, because you have it as an exponential form. Okay, so one common trick that people use in in solving these constrained optimization problems of this form, where you have this pi greater than or equal to 0 constraint, is you just ignore it. Okay, so in that sense, like, you just assume that this constraint doesn't exist, and you just try to proceed as though it doesn't exist and see what you get. Because many times what happens is, if you ignore this, it would be that this whole term goes off, right? So let me just remove. So this whole part goes off and you won't have this lambda. Okay, but still you will have that, this is it's still greater than or equal to 0. So these constraints actually don't really matter. So for many problems, this is some trick that people often do. So the reason why they do is, it reduces the number of variables, so you don't have to really go and find the lambdas here. Okay, so that's the reason why they simplify it. So let's just see this. Let's just ignore the lambdas and see what you get. So this is now, so this is 1 by e power mu plus 1, right? Okay, so yeah, so pi is just this, and you want feasibility, so you want all the p's to sum to 1. Okay, so so what will you get? Can you tell me? So from that you should be able to get the mu, right? So
n upon exponent mu plus 1 is equal to 1.
so n by exponent e power mu plus 1. So e power mu plus 1 is equal to 1, right? So so e power mu plus 1 is n. Okay, so what this is telling you is pi is just 1 by n, right? So e power mu plus 1 is n, so pi is just 1 by n. Okay, and mu also you can solve from here, it's just log n minus 1. Okay,
Yes.
so this is a Kkt point. I mean, this is the optimum value of pi because it shows up in a Kkt point. Okay, so if you find the mu's, it's log n minus 1, and here mu is anyway unrestricted, so the sign doesn't matter. Okay, so but anyway, it's greater than 1. So anyway, so the result you got, the optimum distribution here, which maximizes the entropy, is just pi is 1 by n. So you give an equal mass for all the n points. Okay, so yeah, so this is actually a well-known thing in entropy. So if you say that each of the points x1 to xn takes an equal probability. Okay, that's when there is a maximum uncertainty in the system, right? So the entropy essentially captures that fact, and it is quite intuitive to have that the probabilities are 1 by n. This is the maximizing distribution, the entropy maximizing distribution. And the use is that in many cases, like in many models, when you have your priors, the typical thing is to use some distribution which has a maximum entropy. Okay, and because it's kind of a neutral distribution in some sense. Okay, and then you let the data, whatever data you see or samples that you see, you try to adjust the parameters again. But this serves as a prior in many models, and that's why this is of use. Okay, and there is actually a whole theory of these max entropy models in machine learning, and the whole objective is you try to find a distribution with the maximum entropy. Okay, so that's in machine learning, and also entropy is something that's often used in information theory and like encoding some communication channels. Okay, so in that sense, yeah, this is a well-known fact, but optimization gives you this answer. Like it gives you a justification for why this is the case. Okay, so is this something you've seen before about the entropy, the distribution with the max entropy? Have you seen it in the machine learning course or any other course?
I read about this, but I did not have. I had not seen the proof.
Okay. Okay. So yeah. So this is one thing I also wanted to. Yeah, the reason why I wanted to show you this was that I also wanted to show this trick about many times you don't consider lambdas. So if you see many textbooks or in any worked out examples, one thing they would do is ignore this constraint. Okay, so maybe like a little later, I will just try to show you one more example, maybe of the MLE estimator. Even you do the of multinomial distributions, and even there you do something like this. Okay, so let me just move on. So we saw this Lagrangian functions, and we saw these multipliers. Okay, so these lambdas and mu's and all that. So is there some interpretation, the further interpretations of these multipliers? Of course, it's helping us to solve a constraint optimization problem, but is there something more that it tells us? Okay, so that's what we will do for some time now. So it turns out that it also gives some idea of the effect of perturbation of a constraint. So this idea is something we saw in the context of LPs when we talked of duality. Okay, so the Lagrangian multipliers in this context, it turns out that they give you some idea of how the objective function will change if you change some constraint. Okay, and this theory is also referred to as sensitivity analysis. So if you read some textbook, it's going to be referred with this name. Okay, so let's consider a problem like this where you're trying to minimize some function and you only have inequality constraints. So gix is less than or equal to 0. Okay, so some region like this. So I have 3 constraints in this figure. Okay, and all these curves correspond to g1x is 0, g2x is 0, and so on. Okay, and for this problem, this is the original problem, and this region which is shaded gives the region where gix is less than or equal to 0. Okay, and suppose the optimum is at this point, x star. Okay, and at x star, there are 2 constraints which are active. So g1 and g2 are active. So I've written something here. So if x star is the optimum point, and suppose it's regular, and the active constraint is g2 x star is 0, and also g1 x star is 0. Okay, so there are 2 active constraints. Okay, and we also have g3 x star is strictly less than 0. Okay, now what I'm going to do is I'm going to change the constraint a little bit. I'm going to change the second constraint, this g2x equals 0. I'm just going to push it a little away so that I have g2x equal to epsilon. That's the new constraint. Okay, so that's the new curve. So in terms of the constraint, so I have a new constraint now. So it's going to be, let me call it g2 tilde. So that is g2x is less than or equal to epsilon. Okay, so this is a new problem where everything else is remaining the same. So it is minimize fx subject to g2x less than or equal to epsilon, g1x is less than or equal to 0, and everything else remains the same. The only thing I'm changing is one constraint, g2x. Instead of saying it's less than or equal to 0, now I want it to be less than or equal to epsilon. Okay, so suppose now the new optimum is, let me call it x tilde star. Okay, so the optimum for this problem is x tilde star. And the optimum is such that even at this point, it's these two constraints are the active constraints. Okay, so the original problem was something, and I had x star as the optimum, and at that x star I had some active constraints. Now for the perturb problem, x tilde star is the optimum, and the active constraints still remain the same. So what it means is that at x tilde star I have g1 x tilde star is 0, and g2 of x tilde star, now g2 x tilde star is exactly equal to epsilon. Okay, so that's what it means when I say that these two constraints are active, and g3 x tilde star is less than 0. Okay, so suppose this is the case. Okay, so let's just see what I can tell about the new function value and how it compares with the older function value. Okay, so before that, let's just see how these things relate. So because x star is the optimum for the original problem, so x star is optimum for the original problem. So, and it's a regular point. So what we have is x star should appear in a Kkt point. Okay, so what it means is gradient of fx star. There is some lambda, some multipliers, lambdas, and so it's only inequality, so it's just lambdas. So gradient fx star plus lambda I, so lambda, let me say lambda 1 gradient g1 x star plus lambda 2 gradient g2 x star equals 0. Okay, so lambda 3 g3, that's also there, but since g3 x star is less than 0, this lambda 3 will just become 0. Okay, so this is what essentially it would boil down to, because x star is an optimum. Okay, so what I have is now an expression for gradient of fx star. So I can write this as minus lambda 1 gradient g1 x star minus lambda 2 gradient g2 x star. Okay, so this is for the original problem, we know this. Now for the new problem, what we have, let's try to see what we know. Okay, so in terms of g1, so I'm just going to do something else now. So what I will do is I'll just write g1 x tilde star. So using the Taylor series around x star. Okay, so the idea is you change this constraint by a very small epsilon so that the Taylor series approximation is still valid. Okay, so g1 x tilde star by the Taylor series approximation is approximately g1 x star plus x star minus x tilde star minus x star transpose gradient g1 x star. Okay, so this is the first order Taylor series approximation. Now g1 is an active constraint at x star, so this one is 0, and at x tilde star also g1 is active, so this whole thing is equal to 0. Okay, so what this means is now the second term also has to be 0. So what you get is x star minus x tilde star minus x star transpose gradient g1 x star is equal to 0. Okay, so this is one thing I have. Okay, now if I do the same thing for let's say g2. Okay, so g2 is the one that got changed. Okay, so even for g2, what I'm going to get is g2 x tilde star. I'm just going to use again the Taylor series approximation. So g2 x star plus x star minus x star transpose gradient g2 x star. Okay, so for the original problem, g2 x star was 0 because x star was active at this constraint. Now for the new problem, this is still an active constraint, but now the value of g2 of x tilde star, this whole thing is equal to epsilon because the constraint got perturbed. Okay, so now what this means is that x tilde star minus x star transpose gradient of g2 x star is epsilon. Okay, so this is one more fact. Okay, so now let me try to relate finally the function values. So if I try to again do this for f of x tilde star, so this is going to be approximately f x star plus x tilde star minus x star transpose gradient of fx star. Okay, so now one thing you know is this value x star minus, I mean this gradient fx star, because we knew that x star was optimum for the original point, we had this condition, okay, because it would be a Kkt point, so that's why this is true. Okay, so let's just substitute that here. So I'll just bring this fx star to this side. So what you're going to get is f x tilde star minus fx star is x star x tilde star minus x star transpose gradient fx star, which is minus lambda 1 gradient g1 minus lambda 2 gradient g2. Okay, so this is minus lambda 1 gradient g1 x star minus lambda 2 gradient g2 x star. Okay, so yeah, so now what we have is in this expression here, we just wrote these, we derived these forms, right, from the Taylor series approximations. So x tilde star is for this constraint g1 x star, which is active but which has not been perturbed. This term x tilde star minus x star times gradient, this quantity is 0. Okay, and what remains is just this. So it's just x tilde star minus x star transpose gradient g2 x star times minus lambda 2. Okay, so I hope this is clear. And now from here, this quantity is epsilon. Okay, so what you have is this is minus lambda 2 epsilon. Okay, so the left hand side is the difference in the function values. So this is the optimum value for the original problem, and this one is the optimum for the perturbed problem, and the difference. And this is the quantity by which the constraint changed. Okay, so these Lagrangian multipliers, so minus lambda 2 is just giving you this rate, right? So fx x tilde star minus fx star by epsilon. Okay, so this is giving you some notion of the rate of change of the optimum value of the function with a perturbation. Okay, so this is in some sense like what you saw in duality, right? Like you had some multipliers there, and even those dual variables gave you the, how much the function, the objective changes if you change the constraint a little bit. Okay, and a similar thing is what is given here by the lambdas, the Lagrange multipliers. Okay, so we'll see later that so these Lagrange multipliers also have something to do with the dual of the constrained optimization problems. In general, it's these dual variables which have something to do with the perturbation. Okay, so this is for these active constraints. Okay, so if you can see this in general, for if you have multiple active constraints also, you will see this phenomenon occurring. So the idea is you change the constraints so that only one of them changes, the others remain the same, and the change is very less, so that the optimum, the new optimum that you have, also satisfies things. I mean, even for the new optimum, the same set of constraints are active. Okay, so I'll just pause here. The class has been extremely quiet. So are there any questions? Is this part clear? Is this not clear? Is there something? Yes, Siddharth?
When we perturb one constraint and we sort of expected that x will not change very much because we use that assumption in our Taylor series approximation that it is very close to the initial point.
Yes.
So is there something which is enforcing this sort of well-posedness of the problem, that x will not change? Because it might be, I like hypothetically I cannot think of an example, but it might be the case that perturbing one constraint will make your x go very far.
Yeah, so the idea is you perturb it by a very small amount. this epsilon is a really small amount. I mean, if you change it very drastically, that things change. I mean, the whole the optimum point itself changes by a very drastic amount. Then these things won't hold. But in essence, what is happening is, because these functions are all very smooth, right? I mean, the assumption we make, maybe we've not spelled it out, but the implicit assumption made here is all these functions are continuous. Okay, so only then when can you apply things like the gradient and all that. Okay, so the implicit assumption is all these functions are continuous. So because of that, you have that, if you change it by a very small amount, things don't change too drastically. Okay, so yeah, so that would hold because of this continuity assumption. But yeah, if something changes, if the region is not continuous and all that, then there is no guarantees about these things. Okay, and of course the amount by which the epsilon, I mean, how much can you push that epsilon, that also it would depend on the function. Okay, but in general, if it's like a very small range around the function, around the x star, then that's where all these things hold. Okay, so it's in some sense like how sensitive these constraints are. I mean, how sensitive your optimal point is to these constraints. So that's what it's trying to measure. So if even if you, sometimes it could happen that even if you change by a very small amount, you get huge benefits, right? So if the lambdas are very large, like we saw some example in the context of LPs. So if the lambda 2s are very large, then this difference is going to be huge. Even though you change by very small epsilon, this difference can be very large. So that's the idea. So for some cases, if you change by very small epsilon, you are in that vicinity, but you can get a huge benefit by changing the constraint by even small amounts, right? So that's the whole idea with which this perturbation concepts are analyzed. Okay. Siddharth, did I answer your question?
Yes, ma'am. And ma'am, in the context in which we did this derivation is of convex minimization problems, right?
No, this does not require any convexity. So this holds even, it holds for any problem.
Ma'am, but we used FN only if where we said that optimal point is only if it's a KKT. So doesn't that say that it should be?
No. So what we are assuming here is x star is an optimum point and it's also regular. Okay, so that we are assuming. So there is a KKT, so it will satisfy the KKT condition. So it's only using the necessary conditions. Right?
Okay.
We also make this assumption that it is regular.
Ma'am, I was a bit confused in this. Can you please clear it out that regular, if for any general problem, if the optimal point is regular, then it implies that it should also be a KKT.
If the optimum point is a regular point, then it will appear in a KKT point. It will satisfy the KKT conditions. Right? Siddharth?
And if it's not regular, then it still can be KKT, but we cannot say for sure.
Yeah, if it is not regular, then so there are different things, right? So if there could be that x star is an optimum point, it could be that x star is optimum, but it's not regular. So in that case, we cannot tell for sure whether it will satisfy the KKT conditions. Okay, so we saw some examples of that. Now, if it is if you might also end up just satisfying the KKT conditions for a non-regular point. That can also happen. It may not be an optimum in general. Okay, and so if you have a KKT point, the only time when, I wouldn't say the only time. So if you get a KKT point, then you're sure that it's optimum when the problem is convex. Okay, so
yes.
So if you have that it's optimum and the point is regular, then you're sure that it will satisfy a KKT condition. It will satisfy the Kkt conditions. Now, even in convex optimization problems, which don't satisfy, I mean, if there could be the case that, X star is optimum, but it doesn't satisfy this regularity or even those latest conditions. So then in that case, you're not guaranteed, even for convex problems, you're not guaranteed that you will find a Kkt point. Okay, so that was this example that we had. I kind of left it as an exercise. So this problem here, so in this case, there is an optimum. The function, I mean, the optimization problem is a convex optimization problem. And there is an optimum point here, but it doesn't satisfy these latest conditions, and it doesn't satisfy this regularity also. So then you won't be able to find a Kkt point here. Okay, so even for convex optimization problems, like what is the guarantee that you will find a Kkt point? That comes with some conditions. But suppose you just manage to find a Kkt point somehow, then for convex optimization problems, that is an optimum. Okay, but for other cases, you cannot tell. Okay, Siddharth, is it clear?
Yes, ma'am, it's clear.
Okay, cool. So, yeah, so the next topic I want to start is duality, but maybe I'll just give you one more example of, these MLE estimations, okay, how you use this constrained optimization in the context of ML. So one thing was this max entropy distributions. Now, another example, I just want to, you probably saw it in your machine learning class, but I just want to put it in context here. So estimating the parameters of a multinomial model. Okay, estimating the parameters of, so let's just say it's a maximum likelihood estimation for a multinomial distribution. Okay. Okay, so let's just take this. So here the problem is maybe something like you have a document, okay, and there are a lot of words in the document, and you want to estimate what is the probability of occurrence of each of these words. Okay, so let me say that there are some W1, Wn. So these are the words in my vocabulary, and my document has, so I'll call this the sample. So the document has the words like this, x1, x2, and so on, up to some, let's say xt. Okay, so these are the words that appear in my document, and I'm assuming that these words, the way it comes up, it's just they're showing up independently. So I'm just collecting it together. Like I take a document and I look at all the words that appear in it. Okay, and I just want to estimate what is the probability of each of these words. So this x1 to xt contains these words, w1 to wn, and nothing more. And I want to see what's the probability of w1, what's the probability of w2, and so on, up to the probability of wn. Okay, so a very natural way to do this is what is called a frequentist estimate, where you take the number of occurrences. So if you want to find p1, you see the number of occurrences of W1 in this document, and you just divide it by the total number. So you see the fraction of times W1 came. So that is an estimate for P1. So why is it a good estimate? Okay, so that's why does it make sense? And to know that you can use optimization to see that. Okay, so let me just write it here. So probability P1, so Pi is probability that some x is equal to Wi. Okay, so in some sense, this is you can think of these as realizations of a random variable x, which take W1 with probability P1, W2 with probability P2, and so on. Okay, so this is the probability. Okay, and so on up to Wn with probability Pn. So you can think of these as realizations of these x. Okay, so now if you have this whole document, the likelihood of seeing this d, so likelihood, this function what would that be? It's just the probability of seeing x1 times probability of seeing x2 and so on up to probability that you see xt. So of course there's a given that you know the p's. Okay, so this x2 given p and so on, xt given p. Okay, so because you're assuming that these words show up independently, so this is called a bag of words model, and this is a model that it's used often in natural language processing. Okay, so this would in turn be like, if I have to write it as a product, this would be product for I equals 1 to t. Okay, so the t words that appear I take, and I'm going to look at all possible words. Okay, and I'm going to say that this is the probability that xi takes the value wj, okay, given p, and I'm going to also introduce some variable like this. So yij is 1 if xi, the word xi, the ith word, takes a value of wj. If the ith word is wj, then xij is 1, otherwise it's 0. Okay, so for each word in my document, exactly one of the yij's is 1. So if I take the first word, x1 if I take, then at only one of y11 to y12, y13 like that up to y1n I will take, and exactly one of them is 1. So what this would mean is also this will satisfy that y summation yij is 1. If you sum over all the j's, and this is true for every word in this document d. Okay, so for every word I, this is true. So it's the likelihood is just this product power yij. Okay, so what it means is, let's take an example. If my document, if I have 3 words, so w1, w2, w3, this is my collection, and my document was say w1, w3, w3, w2, w2, w2. Okay, if this was my document, now the likelihood would be what? So this probability of seeing w1 was p1, probability of seeing w3 was p2, and we saw it twice, so this is p2 square, and this is p3. This is p3 square and p2 cube. Okay, this is what would be the likelihood, and so that's exactly what you're going to get if you evaluate this product. Okay, so is this something you saw in your ML class? You might have seen it initially, right? Did you see this? Yes. Yes, so I think you might be familiar with this way of writing things. So let me just move on. So the usual thing is to take a log likelihood. So instead of working with the likelihood, you just take the log of this. So I'll just call it L of P. So L of P, when you take the log, it's just these all become summations. So this will just be I equals 1 to T, J equals 1 to N. And so this quantity here, this is actually Pj. So probability that Wj shows up, so that is this Pj. So this is Yij log Pj. Okay, and so what you're trying to do is maximize L of P, maximize this quantity. So maximize this subject to Pj's is 1, summation of Pj's is 1, and Pj is greater than or equal to 0. So this is the constraint optimization problem that you try to solve while getting a maximum likelihood estimator. Okay, and so even like I showed you for the entropy maximizing example, you could start off by ignoring this constraint, this Pj greater than or equal to 0. Try to write the Kkt conditions and see if the resulting Pj's, if that is going to give you a value greater than or equal to 0, then you're done. Okay, so here this is also a convex optimization problem because it's maximizing a log function, so that is concave. So in terms of the format we have, it would be minimize minus summation I equals 1 to t, summation j equals 1 to n, yij log pj, subject to summation pj is 1, and Pj is greater than or equal to 0. So this is the problem. Now you can try writing the Lagrangian for this problem, and what you will ultimately get is Pj is equal to the number of times the word shows up. So maybe let's just do it quickly. So Lagrangian with respect to P, and there's only one constraint now. So P mu is equal to minus Yij log Pj. So this is summation over I, summation over j, plus mu times summation Pj minus 1. So if I take the derivative with respect to Pj's, what I'm going to get is just you take all the Yij's. So minus Ij, Yij by Pj's plus mu equals 0. Okay. So what this is going to give you is Pj is just summation over I, summation over j, Yij's by mu. Okay, and because all the Pj's have to sum to 1, this mu is just going to be summation. So I think I made a mistake here. There's no summation in this part, right? Because you're taking the derivative with respect to j. So here it's just going to be Yij, and mu is just going to be the summation over all these quantities. Okay, so that to ensure that summation Pj is 1. Okay, so what this would give you is, if you look at it, Yij is 1 if the ith word is the same as Wj. So this numerator here is giving you the number of occurrences of the word j. Okay, and mu is the total count, the total number of all the words. Okay, so that's why this is a reasonable estimate, like taking the ratio of number of times the particular word occurs. Okay, so I think I'll stop here. So I just wanted to illustrate some examples where the constraint optimization shows up. Now in the next class, we will look at duality in the general framework. Okay, so thanks for being here. I will end the class. I'll just hang back for some time if you have doubts. Otherwise, thanks for being here.
Thank you, ma'am.